Here we have function number 2. G of x equals e to the x times x squared minus 3. And we're going to follow the same analysis as before. I'm going to give you the first derivative and the second derivative so that we don't have to waste time trying to find those out. I'm going to trust that by now you know exactly how to handle that nicely. So here is pretty much applying the product rule in order to find those derivatives. Pretty straightforward. So we will begin with analysis number 1, which is the domain of the function. If you notice, e to the x exists for all values of x, and this quadratic x squared minus 3 also is defined for all values of x, so the product is defined for all values of x. So then the domain of our function g is going to consist of all real numbers from negative infinity to positive infinity. Now we're going to go ahead and do the x-intercepts. For the x-intercepts, we know that we're going to let y equal to 0. That means e to the x times x squared minus 3 equals to 0. However, e to the x, if you think of the graph, is never 0. So then if this product is going to be 0, it will be because of x squared minus 3, not because of e to the x. E to the x, and I'm going to make a note of that, e to the x right here is never equal to 0. So then that implies that x squared minus 3 is equal to 0. X squared is equal to 3. So x is equal to plus or minus square root of 3. So we found two x-intercepts. Negative root 3 comma 0 and positive root 3 comma 0. Now we're going to do something similar but with the y-intercepts. So what are the y-intercepts or intercept? They may just be 1. For the y-intercept, we're going to let x be 0. So then that means that g of 0 will be e to the 0 times 0 minus 3. So then that's going to just be negative 3. We found one y-intercept, the point 0 comma negative 3. That's how easy it is. You notice that this function doesn't have denominators at all. It's just a product of two factors with no denominators. So then that means that there's no danger at all of having vertical asymptotes. So I'm going to say over here that for vertical asymptotes, we have exactly none. No vertical asymptotes whatsoever. Now for horizontal asymptotes, remember that we are evaluating a limit at positive or negative infinity. So what is the limit? As x approaches positive infinity, we're going to do that first, and then we're going to do negative infinity. We're going to have to treat them separately here. Because why separately? If you remember in the previous example, we didn't. We kept plus or minus throughout. But in the previous example, the function was a rational function. And this is how we handle rational functions most of the time. Now here, the function that we have is not a rational function. So I have to be more careful and I have to analyze each direction separately. So the limit as x approaches positive infinity of e to the x times x squared minus 3. Notice that as x goes to positive infinity, we know that e to the x goes towards positive infinity. And we know that x squared minus 3 goes towards positive infinity. So then when I multiply two quantities that tend to positive infinity, the product goes to positive infinity. So in other words, having infinity times infinity, that is not an indeterminate form. I know that this limit will be positive infinity. Now what happens in the other direction? The limit as x approaches negative infinity of e to the x times x squared minus 3. In that case, as x approaches negative infinity, e to the x approaches 0. And this quadratic approaches positive infinity. So now I have a situation of 0 times infinity. And this form is considered an indeterminate form because, again, we don't know what is 0 times infinity. We can't say that is 0. We can't multiply infinities because infinity is just a concept. But it is not a form that allows me to use L'Hopital's rule. So then I'm thinking that maybe I can manipulate this expression as we did in the previous section in such a way that I get the indeterminate form that is required in L'Hopital's rule. I want to get 0 over 0 or infinity over infinity. In order for me to do that, I'm going to have to rewrite my function, however. Maybe rewrite it like this. The limit as x goes to infinity, negative infinity of x squared minus 3 divided by 1 over e to the x. I want you to notice how I have not changed the function. I just changed how it looked. But if you take this over 1 over e to the x, you get this expression right here. What is really nice about this is that if I rewrite it, let me rewrite the denominator. Instead of saying 1 over e to the x, I'm going to have e to the negative x. If I do that and I try again, seeing what happens as x goes towards negative infinity, I'm going to get that the numerator is going to go towards positive infinity and the denominator right here. The graph of e to the negative x looks like this. Something like that. So this is y equals e to the negative x. So this is really telling me that as x approaches negative infinity, look at the y values of the function. They're approaching positive infinity. So I am going to get that the bottom is approaching positive infinity. So then the entire expression is approaching infinity over infinity. And this is exactly one of the conditions that will allow us to use L'Hopital's rule. So now using L'Hopital's, we're going to go ahead and differentiate. We're going to have the limit as x approaches negative infinity. The derivative of the top is 2x divided by the derivative of the bottom, e to the negative x times negative 1. So then that means that we're going to have the limit as x approaches negative infinity of 2x divided by negative e to the negative x. And then if I try taking the limit, again, I'm going to see that as x goes towards negative infinity, the numerator is going to go towards negative infinity. And the denominator, let me go back to this graph right here. As x goes towards negative infinity, e to the negative x goes towards positive infinity. So I am going to get that the denominator is going to go towards negative infinity right here. So then the entire quotient is going to go towards infinity over infinity, which means that I can apply L'Hopital's rule a second time. So this will be equal to the limit as x approaches negative infinity of 2 divided by negative e to the negative x. So then trying this again, remember that e to the negative x tends to positive infinity in this direction. So this is getting this, the denominator is going towards negative infinity. That means that the entire quotient is going towards 0. So this limit is going to be equal to 0. So then that implies, we're going to say over here, therefore, the line y equals 0, in other words, the x-axis is a horizontal asymptote. So we know that we have an asymptote, and it's going to be the y, the x-axis. The x-axis will be the horizontal asymptote. Now we're going to go ahead and examine critical points. So in order to do that, just as before, you know that we have to consider the cases where the derivative is equal to 0 and the derivative is undefined. So I'm starting here with the derivative by setting the derivative equal to 0. Again, as before, we know that e to the x is never going to be 0. So if this product is going to be 0, it will depend on the quadratic. So from here, we will say that this implies that x squared plus 2x minus 3 will be equal to 0. And then we notice that the quadratic is factorable. That means that we're going to have x plus 3 times x minus 1 equals to 0. And this means now, this implies that x is equal to negative 3, x is equal to 1. Now, to make them official, critical points where we are going to have the possibility of a local max or a local min, I have to make sure that the function g is defined at negative 3 and 1. If you remember, g of x is e to the x times x squared minus 3. That means that g is defined at negative 3 and 1. So I am going to say that over here, since g is defined at negative 3 and 1, then they are valid. They're valid critical points. So in order to determine whether they're going to be local maximum, local minimum, I'm going to go ahead and do the first derivative test. So I'm going to do the number line and then evaluate the sign of the first derivative in the appropriate intervals. Just as before, you can see my number line here for the first derivative, negative 3 and 1, the critical points with a heavy dot because the first derivative is 0 at negative 3 and 1. And here I have the expression. Now I am going to consider the three intervals, this one here, this one, and this one right here. And what is really nice is that e to the x is always going to be positive. So I will only analyze the sign of the derivative by using my two factors. I'm going to choose a test point on the left of negative 3, something like negative 4. And I'm going to plug in negative 4 here for x and here as well. So let's see. Negative 4 plus 3 is going to be negative. Negative 4 minus 1 is negative. A negative over a negative is going to give me a positive. So I'm going to write over here positive and positive. That means that my graph is increasing in this interval because the first derivative, g prime of x, is greater than 0. Now we're going to go ahead and do the same thing for this interval. Let's choose 0. That's an easy one. So if we do 0, we're going to have 0 plus 3, which is positive. 0 minus 1 is negative. A positive times a negative is a negative. So I'm going to put minus signs. Then that means that my graph there is going to be decreasing because the first derivative is less than 0. Now we're going to go in this interval right here. And let's say we're going to choose 2. If we plug in 2 for x and 2 for x, we're going to have 2 plus 3, that's positive. 2 minus 1, that's positive. A positive times a positive will give us a positive derivative. That means that my graph again is going to be increasing because g prime of x is bigger than 0. So then what is that telling me about local max and local min? Since the derivative changes from positive to negative, then that means that I'm going to have a local maximum. And here I'm going to have a local minimum because the derivative changes sign from negative to positive. So now I just want to go ahead and write that down. Here I have gathered all that information. I have that g is increasing in these two intervals. G is decreasing here. G has a local max at x equals negative 3 and g has a local minimum at x equals 1. Now we're going to go ahead and proceed with the second derivative test. We're going to have the number line for the second derivative, and we're going to examine the sign of the second derivative. We are going to begin with points of inflection. Points of inflection happen where the second derivative is equal to 0, the second derivative is undefined. I'm going to start by setting the second derivative equal to 0. You notice that In fact, if you remember, this was the second derivative, e to the x times this quadratic. Again, e to the x is never 0. So if the second derivative is equal to 0, it's all because of the quadratic. So this is why I am setting this quadratic equal to 0, and then I'm going to try to solve. Now, this quadratic is not factorable, so we are going to have to use the quadratic formula. I already set up the quadratic formula. You can see it right here. I have substituted all the a's, b's, and c's, the coefficients of the quadratic equation right here, onto the quadratic formula. I did a little bit of algebra, simplified, and I got this as my two solutions. Now, because I'm going to be sketching, I rounded those solutions. The first one is approximately 0.2, and the other one is approximately negative 4.2. Now that I have that, I can go ahead and set up the number line for the second derivative test. You can see it right here, for instance. And I'm going to start again with my test points. Now, before I do that, I want to put a closed dot on negative 4.2 and a closed dot on 0.2, indicating that the second derivative is equal to 0 there. So now these are my intervals. This is one interval, another one, and a third one. I am going to analyze concavity there. So I'm going to choose, let's say, a test point like negative 5. And I know that e to the x is going to be always positive. So now, if I take negative 5 and I substitute that into x squared here and 4x, when I do the calculation, and you can do this with your calculator, you're going to get that this expression will end up being positive. And I know that a positive times a positive is a positive. So I'm going to have over here positive, which means that my graph is going to be concave up. Now we're going to go ahead and choose 0 as a test point. When we do that, imagine that I plug in 0 in x squared, 0 here in place of x in the second term. I am going to have just negative 1. A positive times a negative is going to give me a negative. So my graph here is going to be concave down. And then when we go now and choose a test point like 1, we are going to have again positive for e to the x. 1 plus 4 minus 1 is going to be positive. A positive times a positive is a positive. So then this graph is going to be concave up in this interval. So here the second derivative of x is bigger than 0. The second derivative of x is less than 0. The second derivative of x is bigger than 0. Now, what I want is to carefully state the intervals of concavity. So I know that g is concave up precisely in the intervals from negative infinity all the way to negative 4.2, and is also concave up from 0.2 all the way to positive infinity. And it is concave down from negative 4.2 all the way to 0.2. Notice that the second derivative is never undefined. Never undefined because the second derivative is right here, is made up of e to the x, which is always continuous, and this quadratic, which is always continuous. So if we are going to have possible points of inflection, they are just going to come from setting the second derivative equal to 0. And we already found those values as 0.2 approximately and negative 4.2. Now let's settle whether these 2 points are in fact official points of inflection. To be official points of inflection, concavity has to change around those points, which it does. Notice how concavity changes. Concavity changes right here at around negative 4.2 and also around 0.2. So that condition is satisfied. And also, we have to check that g is continuous at those points. Well, g is e to the x times x squared minus 3, if you remember. So g is definitely continuous at those points as well. So then they are official points of inflection. We're going to say over here, therefore, g indeed has points of inflection at x equals, instead of using 0.2 and negative 4.2, I am going to use the exact form, negative 2 plus or minus square root of 5. So G, in fact, has points of inflections at these 2 points because we're going to say G is continuous at those values of x. G is continuous at those values of x, and G changes concavity at those values. So both conditions are satisfied. So we found 2 places, 2 values of x where G is going to have points of inflection. On my next slide, I'm going to go ahead and now and collect all of my points so that I can start the sketch of the graph. Here you can see that I have collected all of those important points. I have the x and the y intercept. I have the y value at negative 3. That was a local maximum, the local minimum, then the points of inflection. I have 2 of those. And then just as a reminder that the x-axis is a horizontal asymptote. So now we can start our sketch. So then, beginning with the intercepts are located at negative 1.7, let's say somewhere here, and 1.7 somewhere here. And then the y-intercept is at 0, negative 3. So 1, 2, and 3 right here. So this will be the y-intercept. Now we're going to go ahead onto the local maximum and minimum point. The local maximum will be at x equals negative 3. So this is negative 2, negative 3 is going to be right here. And then 0.3. So very low right here. And then the local minimum will be at x equals 1. And then the y value is going to be negative 5.4. So negative 3, negative 4, negative 5, negative 5.4. That is going to be, let's say, somewhere here. Then we're going to go ahead and do g of negative 2 minus root 5. This is approximately 0.2. If you remember, negative 2 minus root 5, that was this value right here. This value right here was approximately negative 4.2. And this one right here was approximately 0.2. So I'm going to use those approximations to locate my point. Now these are points of inflection. As before, I'm going to draw them in red. So negative 4.2. So this is negative 4 right here. Negative 4.2 will be somewhere here, let's say, somewhere here. And the y value is 0.2. So I'm going to put it very close to the x-axis like that. Then the other one will be at 0.2. 0.2 is going to be again somewhere here. And the y value is negative 3.7. So here is negative 3 and negative 3.7. Let's say will be somewhere here. So now thinking of the concavity of the graph, going back and revisit the number lines where we established the increasing, decreasing nature, concavity, and all that, we can start sketching the graph. Starting from left to right, if you remember on the left part, the graph was concave up. So I'm going to start with a slight concavity upwards. Then at this red point, the point of inflection, the concavity is going to change. It reaches a local maximum there. It continues being concave down, and then it continues through the y-intercept being concave down to the other point of inflection here. Then the concavity changes there, concave up, and then local minimum, and the graph goes down. And then if you remember, the infinite behavior is that the graph goes off to positive infinity in that direction. If you remember, it's worth noting here, I forgot to do that earlier, the limit as x approaches positive infinity of the actual function e to the x times, I think it was x squared minus 3 equals to positive infinity. So this is exactly why you see this movement right here. Now, what is the range? I think that now we are also ready for the range of this graph now that we have a sketch of the graph. If you notice, the range reaches its lowest y value at this local minimum. In fact, this is no longer a local minimum. This is an absolute minimum. So that minimum took place at a y value of negative 5.4. I'm going to write that down. This value over here is negative 5.4. So then I know that the range of my graph will consist of negative 5.4 all the way towards positive infinity. So that becomes the range of my graph. All y values going as low as negative 5.4 and then increasing towards positive infinity. So here it is, the sketch of g of x.